We are looking into two-dimensional systems in which we have a set of differential equations that are based on two variables, defining what the components are going to be for any point here in this phase space in which we have the variables y and the variables x. We have the system fully determines the components of the local rate of change, the derivative. So what we are after here is a full description of the tendencies of any orbits starting at any given point, say for example that point there. And as I said, so at this point these two equations will give a meaning, so two components x and y. Which will have some sort of resultant as a resultant, and that resultant then will determine the beginning of the orbit. Now, you already knew all of this. I wanted to show you how we can use the nullclines, which are the curves that where the derivative is zero for the both components, to predict which direction the flow is going to go. And first we have to draw the nullclines. To draw the nullclines, we make our rate of change equal to 0 and solve for x or y so that we can plot the curves. So say for instance we may have isolated in this equation for x here, we may have isolated the y in function of x, as a function of x. So something like y is going to be some function of x. This, you can do this because of the implicit function theorem, but I'm not going to get to that. What I'm going to do now is I'm going to draw this y as a function of x nullcline. So notice that this is the nullcline that I have derived from the red equation. I'm keeping color scheme here. So let's say that we have a curve that is a nice little cubic, because you know that I like it. So I'm going to do it like this. Now we know that any state in this curve has a 0x component. And so it moves neither to the left nor to the right. It still might have a y component. But before we get to the y component, I just wanted to say that this curve divides then the areas of the phase space that have a positive x component or a negative x component. We know which side is which by solving for the inequality of x dot larger or equal than 0, of course, and then you will get another equation which will give us the area in which the x is positive or x is negative. I'm going to indicate here, and I'll just suggest that the region under the curve is positive and the region over the curve is negative. So that means that our particle subjected to this field with this x component will move to the positive direction of x when it's under the curve, and to the negative direction of x when it's over the curve. I hope that this makes sense to you. This being according to my assumption that the inequality gives us these areas, so this being positive area and this being the negative area of x. Now we know what happens to all the fields underneath this curve, and obviously as we get closer to the curve we get smaller and smaller x until we have to change direction. So this state here is neither going to the right nor to the left, but states very close to it will move towards the right, so the positive direction of x, and states very close to it from the top side of the curve will move to the negative direction. And similarly, if we have now the nullcline that determines the y component. And let's say that it looks like this, for example. I'm going to make it a line. I will also have an inequality that will decide for me what is the area that is positive or negative. On one side of the curve will be positive directions of y, that is, the flow is going to increase, and another direction will decrease the flow. So if now I assume that y dot function is positive to areas over the curve and negative to areas underneath the curve, you can then calculate that at this point here, we will have a gradient that will point the state upwardly. And similarly, if you have some state here in the negative area of y, it will go down. But it will not only go down, it will basically both go down and to the right. Now you have sufficient information in this graph to distinguish now all of the regions, which direction is the state going to go. And this you can do for any two-dimensional dynamical system, just as long as you know where the nullclines are and which region is the positive and the negative region for those specific nullclines. And so let us quickly work out through an example. We start with this system, and we will draw the vector field and representative orbits of the flow induced by this equation. Our first job is to find the nullclines, the curves where the derivatives for the individual coordinates are equal to 0. Let us begin with the x nullcline. For the x nullcline, x dot equals 0. And thus, the flow in x is 0 and changes direction when y equals 0. That is, the x-axis. To decide for the direction of the x component, we solve now the inequality. When is x dot positive? Our question. Well, when minus y is positive, meaning when y is negative. Let us draw this conclusion in the phase space for 4 initial conditions. Here, 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 and here. So x dot is positive when y is negative. So here x dot is positive, and here x dot is negative. So the action on these states on x is states move to the left here, and states move to the right here. The closer they get to the x-axis, the smaller the flow, the smaller the intensity of the flow. And similarly, the further away they are from the x-axis, the larger the flow. Similarly, for the y nullcline. The y nullcline is the place where there is no y component, and that's equal to x equals 0, identical to the y-axis. Our y nullcline is here. The inequality y dot is larger than 0 indicates that positive x translates into positive changes of y. And when we draw this conclusion in the flow, we will find that here y is positive, and here y dot is negative. And so the y component is positive in this side, and negative in this side. The resultant from this field, hence, for these four initial states, will be something like this. Fully determining the directions of the flow in these quadrants. These resultants indicate a rotating flow. The cycle here would look like this. As you're getting close to the y nullcline, you're inverting the y direction. As you're getting closer to the x nullcline, you're inverting the x direction. Again, you're getting closer to the y nullcline, invert the y direction. And here we close our circle. For this linear system, we have static cycles with constant radius for whatever initial condition we may have, with the exception of our non-hyperbolic equilibrium over here. And the Jacobian matrix at this equilibrium would have purely imaginary eigenvalues. And the awesome thing about this is that you can create your own exercises by creating an x and y nullcline as you like. So it's any curve you may dream about of this nullcline that are going to be positive and negative in these directions. Say that this is the y nullcline with positive here and negative here. And that is the x nullcline, where, say, here is positive and this is the negative side. And so you can draw yourself an exercise to the derivation of any vector field that your heart may dream of.